James Webb Space Telescope has to be cold, really cold, minus 233 degrees Celsius cold. So the way we achieve that is firstly by making the telescope open. It doesn't have a tube around it, but what it does have is a huge sun shield, and the telescope sits behind that sun shield. We're also located at a place called L2, 1.5 million kilometers away from the Earth.
Unlike JWST, we can't see infrared light with the human eye, but we can detect it through heat or experience it visually using an infrared camera.
Infrared light, you can sort of think of it like heat radiation. So everything glows in infrared. You know, you and I are glowing in infrared.
A lot of things in space give off infrared light too, like stars, nebulae, and galaxies. But to detect the faint, faraway targets scientists are after, JWST has to be away from the Earth's warm atmosphere.
And the problem is with Hubble is that Hubble is actually quite warm. Hubble is in low Earth orbit, and it's about the same temperature as the Earth. And that means it's actually emitting in the infrared. And that's a bad thing if you want to detect faint infrared light from very far away, because you're swamped by the light coming from the telescope itself. So the James Webb Space Telescope has to be cold, really cold, minus 233 degrees Celsius cold. So the way we achieve that is firstly by making the telescope open. It doesn't have a tube around it, but what it does have is a huge sun shield, and the telescope sits behind that sun shield. We're also located at a place called L2, 1.5 million kilometers away from the Earth, where the sun and the Earth are always on the same side of the telescope.
In this location, the telescope's main instruments can cool to near absolute zero temperatures and receive the infrared light. Then they can take that light and produce images, or analyze the light to learn what materials are present. This is known as spectroscopy, and is a major feature of JWST's science instruments.
We have 4 instruments on the telescope, and these different instruments are optimized to do different things. So obviously the imagers take images of the universe in both the near-infrared and the mid-infrared part of the spectrum. The spectrographs take spectra of different objects in the universe. So spectra are sort of like, you can think of them as like fingerprints of the objects. So spectra help tell us about the chemical components and what atoms and molecules are in the various different things that we're looking at.
Using 2 of these instruments, NIRCam and NIRSpec, and the power of the telescope, one team is going to be able to take images and reveal the composition of individual stars in our nearest large galaxy, the Andromeda Galaxy. Building a telescope that has enough power and sophistication to enable these sorts of projects wasn't straightforward. Engineers had to come up with a completely new design in comparison to Hubble.
So this telescope has this giant mirror, about 6.5 meters across, about 22 feet, and it has a sun shield that's the size of a tennis court. And so it's sort of an odd-looking design, an odd-looking telescope. The reason it was designed this way is because it's so big. It stands about 4 stories tall, so it's too big for any rocket to fit inside, all unfolded in a rocket. So we had to fold it up to fit inside the rocket, and it unfolded once it was in space.
Since spacebound rockets do fail from time to time, over 3 decades of work, $10 billion, and thousands of scientists' work were on the line.
And we have engine start. And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Honestly, the launch was definitely not the hardest part of this mission. So following launch, we had 2 weeks of really intense, complex, complicated deployments to get this telescope unfolded. And I myself, and I think all of us on the team, were really on the edge of our seats to wait for these deployments to happen.
Given its distance to Earth, If something went wrong with JWST's deployments, there wouldn't be repair missions like there was with Hubble.
The deployment of the sunshield was particularly intense. The sunshield itself is 5 layers, and it had to unfold and then deploy the 5 layers. And there were hundreds of release mechanisms on the sunshield that all had to release at just the right time and just the right way. There were quite a few single point failures, so that if one release mechanism didn't work, there would be nothing we could do to fix it. And so this particular part of the deployments, watching the sunshield deploy, was incredibly stressful, but everything went off so well. The engineers have built an amazing, incredible telescope, and after that 2 weeks, I think all of us took a deep breath. There was definitely a big celebration after the last part of the deployments happened.
The launch was so incredibly efficient, using less fuel than anticipated, it extended the mission from 5 years to an estimated 10 to 15 years. Months later, after the instruments had cooled, there were a series of calibrations to make sure everything was aligned.
The primary mirror is made up of 18 different segments, and those segments had to be perfectly aligned once the telescope was in space. And so what we did was point the telescope at a bright star, and then you essentially get back an image of 18 different stars. And so from using that image and sort of tracing the star image to the different segments, we were able to individually move and tweak each segment to get the telescope to align on the star.
Each mirror had to be aligned to within the billionth of a meter to form a single primary mirror. That required making ultra-fine adjustments equal to 1/10,000th the width of a human hair, which took roughly 3 months to complete. It will give scientists the ability to peer into star-forming regions and to witness their birth more clearly than ever before.
We'll be looking back in time between 20,000 and 200,000 years. We will be looking at 3 massive star-forming regions. One is in the Milky Way, our galaxy, and 2 are in nearby galaxies, the Magellanic Clouds. NGC 3603 is a massive star-forming region located at about 20,000 light years away from us in the Milky Way. And it is made up of many stars, many massive stars, some of which are even 100 times more massive than the Sun, but there are many, many smaller stars, stars like the Sun. The Tarantula Nebula is located in the Large Magellanic Cloud at a distance of about 150,000 light years. The Tarantula is a massive nursery of star formation. There are millions of stars there that were just born, and some of them are still being created, being formed. And the third region that we want to study is called NGC 346, is further away still, about 200,000 light years, in the Small Magellanic Cloud, yet another galaxy. In each one of these regions, we will select about 100 stars, and we will look at them very carefully by blocking everything else. We want to get only the light of those that we are interested, so we can disperse the light and produce a spectrum, very clean. But then, with the camera, we will look at the entire regions, and there will be easily millions of stars that we'll be seeing in these parts. We will be looking at the massive stars, but we are particularly interested in stars like the Sun, because those are the most likely ones to have planets around them. The main goal is to understand what is the difference in the way in which stars form in our own galaxy and also in nearby galaxies. But unfortunately, visible light doesn't travel well in regions where you have lots of dust and gas. And the regions where stars are forming are full of dust. So in those regions, it's very difficult for visible light to go through. But infrared light has longer wavelength, so the light rays are able to go around those particles, and we can see light even when there is lots of dust, so we can see through the dust.